This is problem 5 from section 10.6.2, correct?
Yes.
Or 9.6. I don't know, it says 10.6.2 here. I think it's 9.6, whatever. Problem 5. Let's take a look. Let me grab not this pen, because that pen is not the right pen. There we go. So here's what I have. Use Lagrange multipliers to find the absolute extrema of f of xy equal to 4x squared y squared subject to 2x minus 7y equals 5. I'm just going to make a blanket statement right now. The function does not have an absolute maximum.
Yes. That's good.
Correct. And the way you can see that is you can say, well, this is a line, right? And on a line that's not vertical or horizontal, you can make x or y as large as you want. For example, I could find the point something like, I don't know, y equal to 1,000, x equal to whatever x needs to be so that the things cancel appropriately. Like x would be like 3,500 approximately, y would be close to 1,000, but I need to be up. But like, so if x is 3,000 and y is 1,000 or whatever, and I plug those values in here, that function is super big. And I can make x and y kind of as big as I want, as long as they're on this line. I'm not really restricted in the sense that x and y don't have any kind of upper or lower bounds. So that said, we can see that we don't have an absolute maximum. I can also see, looking at this function, the smallest output value I could ever get is going to be 0. So I'm pretty confident that of the points we find, we're going to get maybe 1, maybe 2 absolute minima and no absolute maximum. Well, let's do the process. So Lagrange multipliers are capital L of x, y, lambda is going to be that function there, 4x squared y squared minus, we set this equal to 0, although it's not super necessary, lambda times 2x minus 7y minus 5 equal to 0. Usual setup. And then we take our partials. Lx is 8x times y squared minus 2 lambda, set that sector equal to 0. Ly is 8x squared times y plus 7 lambda, also equal to 0. And there's something here I'm not, oh yeah. So then solve each one for lambda as usual. Lambda is going to equal 8y squared divided by 2. Sorry, 8xy squared divided by 2. And over here, 7 lambda is going to equal negative 8x squared y. So lambda is going to equal negative 8/7 x squared y. We set them equal to each other. Set them equal to each other. We're going to get 4x y squared equal to negative 8/7 x squared y. And don't make the mistake I often tend to make here and divide both sides by x, y. Technically, that's not the right thing to do. We should bring everything to the same side, factor out, and see what we get. So bringing everything to the left, I have 4x y squared plus 8/7 x squared y equal to 0. I can factor out a 4 and an x and a y. I'm left with a y plus 2/7 times x equal to 0. So either x equals 0 or y equals 0 or y plus 2/7 x equals 0. So let's look at x equals 0. So once we have conditions like x equals 0 or y equals 0 or y equals something with x in it, where do we go back to now? Do we go back to the thing we're trying to maximize or minimize, or do we go back to the constraint? We go back to the constraint because it allows us to find the other thing essentially. So looking back at the constraint here, if x equals 0, then we're going to get 2 times 0 minus 7y equal to 5. So y is going to equal negative 5/7. So one of our critical points is 0, negative 5/7. And we can look and see that if we plug that into the function, we're going to get 0. Right? F of 0, negative 5/7 is going to be 0. because it's 4 times 0 squared times doesn't matter. Similar deal for y equals 0. If I plug in y equals 0 to my constraint, I get 2 times x minus 7 times 0 equal to 5. So I end up getting x equal to 5 halves. And y is equal to 0. So 5 halves comma 0 is another critical point. Also gives me a function value of 0. Also an absolute minimum, because again, it's an absolute minimum that is the lowest value this particular function can have, which we can just see because of the nature of it being x squared times y squared. Right? If it was x cubed times y squared, totally different story. Then there's a way we can't just be like, oh yeah, I know 0 is a minimum. And lastly here, setting y equal to negative 2/7 x and plugging into this constraint here, I'm going to get 2x minus 7 times negative 2/7 x equal to 5. So then 2x minus minus is plus 2x, so 4x equals 5, x equals 5/4. And then if y is negative 2/7 x, y is going to be negative 2/7 times 5/4, which is equal to this. Which is equal to, I don't know, negative 5/14. And I don't know what I get. I don't really want to plug that into the function and get something. Is that right? Negative 5/14? Yeah, that's right. But I know that when I plug that in, if I plug that in, f of 5/4 comma negative 5/14 is definitely not 0. It's definitely bigger than 0, because if I plug it into this function, x squared times y squared times 4 is not 0. If these are not 0 each, that's going to be positive. But we know it's not an absolute maximum because of the stuff we said at the very beginning of the problem, which is that along this line, this function can get infinitely large. So it's not an absolute maximum. It is, and I did some inspection on inspection. That was what I was looking for. This problem merits further inspection. That point there, if you look at like the way the constraint intersects the surface, that point at x equal to 5/4 and y equal to negative 15/4 and z equal to whatever the z value is a relative maximum. It's kind of interesting. In fact, let me show you the graph, because I think I have it right here. Because I was really like, I've been thinking about this problem actually a lot, because it's I was intrigued how I don't really know how the TA who worked the solutions for that one problem said like the gradient is this, so we don't have an extrema. I'm still pondering how that actually works, but let's see. Do I have the graph still? Yeah, right there. Oh, sorry. Let me change the sharing. I need to share the whole screen, not just the visualizer. There we go. So here's a graph of a similar situation. I will point out, I will point out that the purple surface is the surface that we're trying to maximize or minimize. I made it 100x squared y squared just to be able to see things. And then my constraint was 2x minus 4y equal to 1 instead of 2x minus 7y equal to 5. Similar idea though, that's in blue. So there's our constraint. And then here are our 3 critical points. X is 0, y is something, y is something, x is 0, and then the one that's kind of the weird one here. And if you look at the weird one there, let me turn this off for a second. We can see that weird one right there, the gray one. Oops, let me zoom. Whoops, oh my gosh. That gray one is a relative maximum. It's not an absolute maximum, right? That function gets way bigger. Whoops, stop rotating. Over here along the curve still, where the blue plane intersects the purple surface. So it's not an absolute maximum, but it sure is a relative maximum. Is that important for this problem? Not really. Is it interesting? Yeah, it's super interesting. Anyway. Oh, and then just to point out the other thing I had graphed there, this plane here, that is the direction of the gradient. So if you look here in the direction of the gradient points in the direction of steepest ascent. And I can't really make a vector here, but you can look here, right? If you look in that direction here, oh yeah, that direction from that point that way is definitely the direction of steepest ascent. I don't know what that being equal to whatever it's equal to actually tells us, because I really don't. Like I've thought about it, I'm like, I still don't really get what that means, but that's what it looks like at least. So that's, in my opinion, the answer to this problem is there are 2 places where we have an absolute minimum value, and the absolute minimum value is 0. And there are no places where we have an absolute maximum because the function just gets larger and larger and larger along the constraint. Which is kind of annoying. But sometimes math problems are annoying. Any questions about that problem? Which I'll try to answer. Oops. All right, well, we're almost done with Lagrange multipliers. And I think after this, we kind of just get to leave them in the dust to be like, bye. Maybe I don't think they come back up on the final, but as is everything, I am not the one who writes your exam, so your teacher is a better gauge of that. Okay. Let's talk about double integrals, which is not in the textbook. So yeah. Double integrals. Interesting. I hadn't thought about this way before. So yeah, let's do this. So let's start off with the following. We want to find the area in quadrant 1 between the curves y equal to 4x and y equal to x cubed. And first, we're going to do this using just a single integral, because that's the way I would have thought of it before I saw double integrals. So let's draw a picture. Y equals 4x looks something like this. It's a straight line. Y equals x cubed looks something like this. If I was going to find the area between these two curves, I would find where they intersected. So setting them equal to each other, x cubed equal to 4x, bring everything to one side, factor out an x, factor even more, and you end up getting points of intersection that are x equal to 0, x equal to 2, and x equal to -2. But we don't care about the -2 because we said we wanted the area just in the first quadrant. So x being negative is not of concern. So we only care about these 2 points of intersection here. That point there when x is 0 and y is 0, and that point there when x is 2 and y is 8. So one way you could write the area of this curve using a single integral is that the area, sorry, one more thing. I like to draw a little vertical rectangle here and think of the area of that rectangle. The area of that rectangle is the base, which is a small change in x, times the height, which is the top function minus the bottom function. So the area, write this up here, the area of the rectangle is the top function minus the bottom function times the width, which in this case ends up being 4x minus x cubed times dx. Notably, the height of that rectangle changes as you slide from left to right. Over here, close to the origin, the rectangle is pretty short. In the middle, it's relatively tall. Over here, it's again pretty short. It depends on where x is, right? If x is 1, the height of the rectangle is 4 minus 1. If x is 1.5, the height of the rectangle is 4 times 1.5 minus 1.5 cubed, whatever that is, probably smaller. And then, as is with much of calculus, with integration, we're going to add up all the rectangles. The way you add up all the rectangles is you integrate. So the area is going to equal the integral from 0 to 2 of the top function minus the bottom function times the thickness. And I don't actually really want to calculate this. I mean, we will. We're going to get 4x squared over 2 minus x to the fourth over 4 from 0 to 2, which ends up being 4 times 4 over 2 minus 2 to the fourth over 4 minus 0, which is 16 over 2 minus 16 over 4, which is 4. A lot of 2's and 4's there. Okay, here's how we do this using a double integral. So you're going to have two integrals. The inner integral, and this one here, the lower limit of integration is going to be your bottom function. And the upper limit of integration is going to be your top function. You're essentially looking at the boundaries, the top and bottom boundaries of this rectangle that we've drawn. So the inner limit of integration here is going to be, the lower limit is going to be y equals x cubed. And the upper limit is going to be y equal to 4x. dy. Which I know might feel kind of weird that it's a dy there, but it is. Oh, question or something in the chat. Can we move the page? Oh, of course. Yes. Sorry. Yeah. Don't hesitate to ask. Yeah. Sorry about that. Let me actually, instead of moving the page down, let me move the camera down. That's probably better. Yeah. Yeah. Because I feel like I'm kind of sliding to the bottom here. Let me try that. That's a little bit better. Yeah. No problem. Anytime. Yes. So there's my inner integral. And then my outer integral is just the limits of integration for the other variable. So I'm thinking of y going from x cubed to y going to x cubed to y going to, oh my gosh. Let me say it again. From y equals x cubed to y equals x 4x. And then the xy's are going as far left as x equals 0 to as far right as x equals 2 dx. What are we integrating? We're integrating 1. So the thing here is really what you're actually finding is not the area of this thing. You're finding paper. Can I find paper? All right here. What you're really doing is you're finding the volume of a shape whose bottom looks like that. So it kind of looks like I'm drawing it like in 2 dimensions here. And then whose height is 1. So we're finding the volume of this. But if the height of something is 1, the volume is just the area times 1, which is the same as the area, just with different dimensions. So that's what we're actually really doing, is we're finding the volume of this shape that has a height of 1, but it ends up equaling the area. Okay, so check this out. This is going to look very similar to what we just did. With respect to y, what is the antiderivative of 1? Yeah, it's just y. Or if it was with respect to x, it'd be just x. But yeah, when you integrate 1, you just get whatever variable you happen to be using. So this is going to equal, now watch this here for a second, the integral from x equals 0 to x equals 2. You don't actually have to write x equals here, just like you don't have to write y equals here, because this being dy implies it's y equals these things, and this being dx implies those are x equals those things, but I like to write it so it's more clear. You're going to get the integral of 1, which is y, evaluated from x cubed to 4x dx. And now when I do that inner integral, or that inner evaluation, I have the integral from x equals 0 to x equals 2. Well, I plug in the top thing first, minus I plug in the bottom thing second. Oh, look at that. That is the same as that integral right there that I used to find the area in the first place. So really, when you're finding the area, it's kind of like instead of integrating the top function minus the bottom function, the top function that you would have written there becomes your upper limit of integration in the inner integral. And the thing you're subtracting, the bottom function, becomes your lower limit of integration in the inner integral. Something to know about double integrals is that the outer limits of integration, I should say definite integrals, they're double integrals, because you could have one that was indefinite, but that's not really what we're doing here. For definite integrals, the outer limits of integration always have to be constants. You can't have any variables in there. Whereas in the inner ones, they typically have variables unless the region is like a rectangle. The region's a rectangle, then you just get x going from constant to constant, y going from constant to a constant. If it's not a rectangle, and most regions are not rectangles, it's going to be some sort of variable thing in the inner integral limits of integration. Lots of words there. I will also point out, we could have set up this double integral in the other order, meaning instead of drawing a vertical strip like this and doing my inner limits of integration being y equals x cubed to y equals 4x, I could have drawn a horizontal strip and have my inner limits of integration being from x equals something to x equals something. Let's do that. So, same region. Same in quotes. And here's y equals x cubed. And over here is y equals 4x. What we're going to do is we're going to go horizontal. So I want to find the area. Well, now my inner limit of integration. So when you do it the other way, you go from bottom to top. Or as I like to think of it, from lesser y value to greater y value, right? Y equals x cubed is the lower thing, y equals 4x is the higher thing. When we do it this way, we go from lesser x value to greater x value, from left to right. So my lower limit of integration, I should solve these for x. Dividing both sides by 4, I get x equal to y divided by 4. Cube rooting both sides, I get x equal to the cube root of y. So my left hand, or my lower limit of integration, is going to be x equal to y over 4. My upper or right hand limit of integration is going to be x equal to y to the 1/3, or the cube root of y. And that's going to be a dx, which I know feels maybe wrong, because I look at that thing, I'm like, well, but it's a strip like this, that's a dy right there. Well, that's because that's the outer part interpretation. I'm really matching this x here with the fact that it's x equals and x equals. That is how I'm thinking of it. And my outer limits of integration are just going to be y equals how low this strip goes to how high this strip goes. And then you don't actually have to write a 1 here. It's implied if it's not there, but I like to write a 1 there. And this would turn out to be the same. In fact, let's do it to see that it's the same. Because we didn't have to do this one because we had already finished it up here as the same integral. Well, let's do this other one to see that we actually do get the same result of 4. So integrating this, the integral of 1 is x, evaluated from y over 4 to y to the 1/3. And then we're going to integrate that from y equals 0 to y equals 8. Stupid smearing pen. So then we get the integral from 0 to 8 of y to the 1/3 minus y divided by 4, or I would probably write 1/4 times y dy. Anti-differentiate, you get y to the 4/3 divided by 4/3, or multiplied by 3/4, minus 1/4 times y squared over 2, from 0 to 8. Not feeling confident this is come out the same, but it should anyway. So you get 3/4 times 8 to the 4/3 minus, let's make that a 1/8 times 8 squared minus 0. That ends up being, I'm really feeling, okay. 3/4 times, what is 8 to the 4/3? What's 8 to the 1/3? What's 2 to the 4th? That's 8 to the 4/3. You do the cube power, the root power first, and then the power part second, or the root first, power second. So that is going to be 3/4 of 16. 1/8 times 8 squared is just 8. 3/4 of 16 is 12. 12 minus 8 is 4. Oh, good, they turn out the same, which they should. So you can find the area either way. You can either set up the integral where you're doing dx first and dy second, or you can set the integral where you do dy first and dx second. It just depends on what kind of strip you want to draw. If this is a dx here, you're using a horizontal strip, you're going from left to right, left to right. If you're using a dy here first, you're going from y equals low to y equals high. Y equals a function of x to y equals a function of x. Okay, let's do a few more examples. And of course, if you have questions, you are always welcome to ask them. So we can kind of go the other way. Say, well, what if I gave you an integral? Let's say we have the integral from 0 to 3, and then from x squared to 9, dy dx, and I wanted to sketch the region. Okay. So I think it's really nice to remember, right? That's y equals x squared. That's y equals 9. How do I know it's y equals? Right, because of the dy, and or because I have x there. It wouldn't make sense to be graphing x equal to x squared, right? That's not the kind of thing we're doing here. So if you see a variable in these limits of integration, it means it's the other variable equal to it. And then here we've got x equals 0 to x equals 3. If you're trying to sketch the region, you always want to draw the functions for the inner limits of integration first. So I'm just going to draw y equals x squared and y equals 9. Y equals x squared. Here's y equals 9. I know that these intersect when x is 3 or when x is -3. But then, and actually, we can even do ourselves one better. We can draw the vertical strip. And we know it's a vertical strip because we're going from y equals something to y equals something. Right? Y equals 9. Y equals x squared. And then our vertical strip goes as far left as x equals 0. And as far right as x equals 3. So this is our region. One thing that's important to be able to do with double integrals is to be able to reverse the order of integration. So to take a region like this, or to take an integral like this, and I will say, as with a lot of things with integration, the best way to do it is to draw the region. So if someone said, here's an integral, I want you to change the order of integration, the easiest way to see how to do that is to draw the region of integration, and then be like, okay, well, now I'm going to take that same region, and we're just going to draw the region on its own with nothing, with no other frills. So there's my region. And instead of using a vertical, wow, I did not draw that really great. All right, okay. Instead of using a vertical strip, now I'm going to use a horizontal strip. My right function here, instead of being y equals x squared, is now going to be x equal to the square root of y. It is the positive square root of y. If I happen to be doing on this left side over here, that would be x equal to the negative square root of y, but we happen to be on the right side, so it's positive. And then this left-hand boundary is going to be x equal to 0. So reversing the order of integration, my inner limits are going to be x equals 0 to x equals root y. That's going to be a dx. And then my outer limits of integration are just going to be, instead of how far left and how far right, how far down, or what's the lowest y value you get, and what's the highest y value you get. We're going to go from y equals 0 to y equals 9. And I suppose I could toss in a 1 here and a 1 here, although you don't really need them. So here's a good question. Why would you do this? Why would I use a double integral to find the area of something when I could have just as easily used one integral and did the integral of the top function minus the bottom function? Because we're going to use the double integral to find a volume, not just an area. We're going to say that we're going to integrate some surface over some region to get the volume under it. Just like in 17b, we integrated some function over an interval to get the area under the curve. We're just kind of extending the idea by one dimension. So that's why we're actually talking about writing these regions in terms of double integral, because to be able to do that, you have to be able to write the area part as the limits of integration of your double integral, and then the thing you're integrating is a function of x and y. So the real reason is volumes. Use double integrals is to calculate volume. I should say calculate volume under a surface. F of x, y above some region in the xy plane, often called R. Cool. Let's look at some examples. So let's say we want to do the following. Let's find the volume of the solid in the first octant. Point of interest, which I may have mentioned before, but I'll say again. The first octant, just like the first quadrant, is the corner of the three-dimensional system where all things are positive. Right? In quadrant one, x is positive, y is positive. In quadrant one, or in octant one, x is positive, y is positive, and z is positive. Unlike the xy coordinate system where we have the first, second, third, and fourth quadrant numbered by going counterclockwise, there is no specific numbering of the other octants. No one's ever going to know what you mean when you say the third octant. There's no like good way of numbering them. You might be able to make, no, I don't know. I'm not even going to say that. I was going to say something, but it's probably not true, so I'm not going to say it. To find the volume of the solid in the first octant bounded by the plane x plus 2y plus 3z equal to 6. And not that you need to necessarily draw the plane, but I want to draw it anyway just so you have an idea of what's going on here. So yeah, sure, I picked the wrong way. So here's my x, y, z coordinate system. And I'll point out that when you graph a plane, one of the easiest ways to graph a plane, if you're able to, is to just plot all the intercepts. Just like if you're graphing a line, if you can plot the x-intercept and the y-intercept, you just draw the line through them. Same deal is true for a plane. If I can find all three intercepts, I can just kind of connect the dots and make a triangle, which is part of a plane. So let's see. If y and z are 0, x is going to be 6. If x and y are 0, z is going to be 2. And if x and z are 0, y is going to be 3. So my plane is looking something like this. So it's a tetrahedron. And the idea here, so just like in 2 dimensions, how we would like draw the rectangle under the curve to kind of estimate that area and then add them all up. Here, we're going to draw the rectangular box under the surface. So maybe like out here, right, there's a little square there, and I'm going to find that square's volume. And I'm going to do that for a bunch of square, right? And then I'm going to just add them all up over the region that's in the xy plane. So the volume of my box there is equal to the height of the box. Well, the height is going, actually just say the height for a second, times the area of the square that's in the bottom there. Times the area that's in the xy plane. Check this out though. The height of that box is just whatever the z value is, because z is height, typically. Solving for z, we would get 6 minus x minus 2y divided by 3. And the area of the little square is a small change in x times a small change in y. It's a dx times dy. just like the area of the rectangle was the height of the rectangle times a dx. Same idea here. Now it's height times dx times dy. So now to find the actual volume, we're going to add up all the rectangles. But you know what? There's not just rectangles in one direction, right? There's one over here and there's one over here, but there's also one over there and there's one over there and there's one, right? There's all sorts of rectangles whose heights I'm not drawing in this triangular shape in the XY plane. So what we're going to do is we're going to say, well, the volume is going to equal the double integral of my function. 6 minus x minus 2y over 3. I haven't decided if I want to do dx dy or dy dx yet. Usually I want to do dy dx. That's more natural for most of us to do. But let's draw the region in the xy plane to see. So if I'm looking in the xy plane, let me say this again. If I'm looking in the xy plane, what's z equal to in the xy plane? If I'm on the ground, z is 0. So to draw the region in the xy plane, all we have to do is let z equals 0. And so I'm just trying to draw the straight line, x plus 2y equals 6. It's really just going to have, I'm really just taking this triangle and making it in the xy plane. But I like to draw it so I can see it. So in the xy plane, I'm going to get, well, x equal to 6 and y equal to 3 are my intercepts. So here's x equal to 6, here's y equal to 3. Wow, there's x equal to 6 and y equal to 3. And so now I'm going to either use, like in all the previous problems we just did, a vertical strip or a horizontal strip. I like to use a vertical strip because that feels more natural. But it doesn't really matter as long as you're consistent. So there's my vertical strip. The bottom of that vertical strip is y equals 0. The top of that vertical strip, I have probably to find the equation of that line. So I know it was x plus 2y equal to 6. So if I solve for y, 2y equals 6 minus x, y equals 6 minus x over 2. dy, and then my strips go as far left as x equals 0, as far right as x equals 6 dx. That's the thought process for setting up a double integral to find volume. You're integrating the z part, the function, the surface, and then you're integrating over the region of integration in the xy plane, which we describe in the limits of integration. And then you actually have to do the integration. So let's actually do it because there is a couple things to be aware of here. So let's rewrite this so it looks a little bit less messy. If I was rewriting this, I would certainly factor out the 1/3 in front of the whole thing. So I'm going to rewrite the volume as 1/3 the integral from x equals 0 to x equals 6, the integral from y equals 0 to y equals, 6 minus x over 2 of 6 minus x minus 2y dy dx. And just like with partial derivatives, when we integrate with respect to a variable, we treat all the other variables like they're constants. But the difference is when we differentiate, and that's the case, all those derivatives just become 0. When we anti-differentiate a constant, you get that constant times your variable, right? The integral of 4 is 4x. The integral of x with respect to y is going to be x times y. So here's what we're going to get. Looking at this first inner integral. We're going to get 1/3 times the integral from x equals 0 to x equals 6. And now we anti-differentiate. So antiderivative of 6 is 6y. Antiderivative of x is xy. Antiderivative of 2y is 2y squared over 2, or just y squared. I do like to write the y equals right here so I know what I'm plugging in for. From y equals 0 to y equals, I would probably rewrite this as 3 minus x over 2, or 3 minus 1/2 x. And then you don't need these parentheses. I just like to be clear what's going on here. dx. So we're just evaluating the inner integral before we do anything else. So plugging in those things here, we're going to get 1/3 integral from 0 to 6. 6 times that So now I see why I didn't want to do that. Oh, it's fine. It's fine. These are always kind of messy. I'm not gonna lie. X times y, which is 3 minus 1/2 x. And finally, minus y squared, which is 3 minus 1/2 x squared. And if you plug in 0, you're going to get 0 minus 0 minus 0. But you do have to check, right? Because sometimes you get like e to the 0, which is 1, or cosine of 0, which is 1. Ugh. We probably have to multiply this all out, which is unfortunate. But it could be much worse. So, be thankful it's not much worse. So multiplying this out, we have 1/3 times the integral from 0 to 6. 6 times 3 is 18. 6 times 1/2 x is 3x minus another 3x. Minus x times minus 1/2 x is plus 1/2 x squared. And then this is going to be minus 3 minus 1/2 x. Quantity squared is going to be 9. Minus 3/2 x minus 3/2 x is minus 3x plus 1/4 x squared. Putting it all together. So let's see. Let's look at our constants first. I have an 18 minus a 9. So that's a 9. I have a minus 3x plus 3x. So that's just going to be a minus 3x overall, right? A minus 3x minus 6x plus 3x gets you back to minus 3x. And finally, 1/2 x squared minus 1/4 x squared is 1/4 x squared. From x equals 0 to x equals 6. Kind of gross, but not that bad. Finally, we anti-differentiate again. We get 1/3 times the integral of all this, which is 9x minus 3x squared over 2 plus 1/4 x cubed over 3 from 0 to 6. We plug in and we get 1/3 times 9 times 6 is 54. 3 times 36 over 2 plus 1/12 times 6 cubed minus 0 plus 0 plus 0. Could you simplify that? Sure. Do we want to? No, we don't want to. We would leave it like this. I mean, yeah, you could simplify that. It probably comes out to be an integer because things will cancel fairly decently here, but that's not the point. The point of this is to be able to set it up and to do the integral. Yeah, the evaluation is a little messy, but that's not really what we're focusing on. Questions? Comments?
If you want to trade,
Yeah, sure. Oh, with trig. Okay, I mean, I said yes very confidently there. Now I have to think of one that is not going to suck.
well, trade or log.
Sure. Yeah. No, definitely not everything's going to be linear. So let me clarify. Are we looking for one where the region we're integrating over has logs or trig, or the function that we're integrating has logs or trig? It's fine if you don't know the answer to that question.
As complicated as possible.
As complicated as possible. That sounds like a bad idea. But there was in class. Oh no, you had the test yesterday. You mean for the test? I see. But there weren't any double integrals in the test.
Yeah.
Okay, all right. Not yet. Next test. Okay, let me think for a second here. Sure. So let's do this next one. I will, yes, I'll come back to that, but there's a couple things we should look at. Yeah, we can do that, but I don't. Oh yeah, sure. This one's good. Let's say we've got the following. Here's a good word problem. So the amount of rainfall per year in the triangular region, triangular region, bounded by the coordinates 1, 0, 5, 0, and 5, 4, is given by the following. F of x comma y is equal to 4 divided by x times y plus 1 inches. Find the total amount of rainfall for the year over that region. or without so many words, find the double integral of this function over the region we described with those points. If I was doing this problem, I would start off by drawing the region that we're integrating over. So normally, the thing I did over here, where I drew my surface, normally we're not going to do that. Normally it's really hard. Like this was, planes are easy to draw. Most other surfaces are not particularly easy to draw. I don't really have a very good idea of what this surface looks like. I certainly don't have much of a chance of drawing it very well because it's hard to draw things in 3D. So we're not going to do that. We're instead going to say, well, let's draw the region of integration because that's actually what we need to kind of make this work. So here's my region in the XY plane. So we're bounded with a triangular region bounded by the points 1, 0, and 5, 0, and 5, 4. There's my region right there. And two of those boundaries are actually really easy to describe. This line over here is the line x equal to 5, the vertical line. This line here is the line y equal to 0. And this line here that goes to the points 5, 4, and 1, 0, we could find pretty easily. The slope there of that line is 4 minus 0 over 5 minus 1, which is just 1. And I can actually use either point. My x-intercept is 1. My y-intercept would be -1. But I could say that y minus the y coordinate is equal to my slope times x minus the x coordinate. So the equation of that line is just y equal to x minus 1. And then you can use any kind of strip you want. Most of us are most comfortable using vertical strips, which is what we're used to. We're thinking of top, we're used to thinking of top minus bottom, and then going from left to right. That's what I would usually encourage. That's what I'm going to encourage here. So the total rainfall is going to equal the double integral over the region, which we're going to describe as, well, the inner limits are the ones we're going from function to function. So my lower limit for my inner limits of integration, my lower limit is going to be y equal to 0. My upper limit is going to be y equal to x minus 1. That's going to go with dy. And then my outer limits of integration, what's my lower value for x? How far left does my strip go? How far right? I think I heard 5. Yeah. Or really, you could just say, what's the least x value you get in the region? What's the biggest x value you get in the region? That's another way. I like to think of it sliding back and forth. Just literally, that's how I visualize it. But if there's a different way of thinking about it for you, that is totally good. And then we have to actually integrate the function 4 over x times y plus 1. Now, here's what I would say. We know we're going to integrate with respect to y first because we have the dy first there. So I would rewrite this function just a little bit as 4 over x times 1 over y plus 1. And I'm thinking of this for the moment as a constant as far as y is concerned times 1 over y plus 1. And when you integrate a constant times a function, that constant just hangs out. Just like when you differentiate a constant times a function, that constant multiple just hangs out. So when we integrate 4 over x times 1 over y plus 1 with respect to y, we're going to get the outer integral staying the same. The integral of this is going to be, well, the 4 over x is going to just hang out. And the antiderivative of 1 over y plus 1 is the natural log of the absolute value of y plus 1. From y equals 0 to y equals x minus 1. Oh, there's a chat. Let's see what's in the chat here. Where did x minus y equals x minus 1 come from? Sure. So when I was doing this vertical strip here, I'm looking at the boundaries of the strip, the bottom and the top of essentially where this what functions that strip hits. And the lower boundary here was y equals 0, and the upper boundary here was the line y equals x minus 1. And we got that by just finding the slope between these 2 points and then using the x-intercept of 1, 0 to find the equation of the line, which was y minus 0 equals the slope times x minus 1, which became y equals x minus 1. That's where that comes from. And then we plug in. So you end up getting the integral from 1 to 5. Now, I'm only plugging in the x minus 1 for every instance of y. That's why I like to write y equals here. So I'm going to plug in x minus 1 and get 4 over x times the natural log of x minus 1 plus 1 is just x. Actually, technically, I can drop the absolute values here since y equals 0 to y equals x plus 1, x minus 1. Those are definitely bigger than 0, and adding 1 makes it even bigger than 0. So I can drop the absolute values there. The only reason I point that is because integrating the natural log of the absolute value of x is kind of weird. So we usually like to make an observation about things being positive or negative. And then plugging in 0, I get 4 over x times the natural log of 0 plus 1. But the natural log of 0 plus 1 is the natural log of 1, which is equal to 0. And I don't really want to write that in here, so I'm just going to leave it there. Oh, we're running out of space. Yeah, we need more space. Okay. So now I would probably rewrite this in the following way. I'd probably rewrite this integral as 4 times, I probably should have brought the 4 out from the very beginning, all the way out in front. I didn't. 1 to 5 of 1 over x times the natural log of x times dx. All right. I see. What kind of method of integration do I need to use? Let me back it up. I see a mixture. I see a logarithm and the power of x. So I only have really one of 2 choices. It's either going to be, well, the opposite. You're thinking derivatives. I'm thinking antiderivatives. So the undoing of the product rule is like integration by parts, or the other option when you have a mixture is U substitution. And sorry, I'm realizing I'm thinking about something I've talked more about my 17B class, not my 17C class. Apologies. I'm saying things like I expect you to know what I mean exactly here. So I'll just say more explicitly here, when you have a function that you're integrating that's a mixture of 2 types of functions, like a logarithm and either a power of x or a trig function or e to the x, we usually call those mixtures because you've got 2 different types of functions. And the way we usually integrate or try to integrate a mixture is by first seeing if U substitution works. And then if U substitution doesn't work, then we try integration by parts. Because usually U substitution is easier. And here U sub will work. If we let U, I'm just going to do the indefinite integral off to the side here. If I let U equal the natural log of x, du is exactly 1 over x times dx. So great. There's my du. So I can rewrite this integral as the integral of natural log of x, which is just u, times my 1 over x dx, which is just du. Cool. Anti-differentiate, you get u to the second divided by 2. I don't even really care about the plus c because it's just my side work. I'm using to help myself out, which is going to be the natural log of x squared over 2. It's coming back over here. This is going to be equal to 4 times, well, the integral of 1 over x times natural log of x is exactly the natural log of x squared over 2, evaluated from x equals 1 to x equals 5. Which you could even write, if you want, God, man, just all over my hand. All right. You can write as 2 natural log of x squared from x equals 1 to x equals 5. Plugging in, you get 2 times the natural log of 5 squared minus 2 times the natural log of 1 squared. But that's 0. So you get 2 times natural log of 5 squared. Cubic inches of rain, right? Because in the beginning of this problem, we talked about how the amount of rain was that many inches. And so if we're getting a volume of rain, it should be cubic inches. All right. what I think is one of the funnest or most interesting things about these double integrals is sometimes you have to change the order of integration to be able to do it, which might not sound particularly fun. It might sound like, well, that's terrible, but I don't know. It just, I find it interesting. So let's do an example. Let's say we have the integral from y equals 0 to y equals 2 of the integral from x equals 1/2 y to x equals 1 of e to the x squared dx dy. Worth knowing, it is impossible to anti-differentiate e to the x squared. Or I should say it more explicitly, e to the x squared does not have a nice antiderivative. There is no elementary function that's just exponentials or logarithms or sines or trigs or whatever altogether to make the antiderivative e to the x squared. You can write the antiderivative e to the x squared. It would be the integral of e to the x squared, which is not super helpful. So we can't anti-differentiate this. There just really isn't an answer, which always kind of bummed me out when I was like, really? There's no one's found it yet. It's not a question of finding it yet. It has been proven that it cannot be done. So there is no like search for the integral of e to the x squared. It's just not there. But we can totally change the order of integration so that we integrate with respect to y first. And integrating that with respect to y is easy because that's just a constant as far as y is concerned. So let's draw the region. And I should point out here, we have to, or we must, change the order of integration. And I will tell you, this is a popular type of question about double integrals. This is what I would certainly ask if I was writing a test. So the region here, well, let's be careful. We've got x equals 1/2 y to x equals 1. I'm not great at graphing x equals a function of y. I know that x equals 1/2 y is the same as y equal to 2x. Okay, I'm okay at graphing that. So y equals 2x is a straight line, kind of steep. And x equals 1 is a vertical line. I guess very steep. And normally, if someone has done the region correctly, the places where these things intersect each other should be your other limits of integration. So this is my left bound to right bound. And then my limits of integration are from y equals 0. And I bet that point there is when y equals 2. And it is, because if x is 1, y has to be 2. Right? If x is 1, y is 2. So here is my region. But now instead of using a horizontal strip like I'm using in this setup here, I'm going to change it to being a vertical strip. So now my new integral, so my inner limits of integration are going to be from a low of y equals 0 to a high of, instead of x equals 1/2 y equals 2x. Still e to the x squared, right? The function you're integrating or your integrand does not change, but now it's a dy here. And then my outer limits of integration, how far left and how far right are vertical strip slides. The slide as far left is x equals 0, as far right as x equals 1. Same region. I'm describing the same triangle, just in the opposite order that I was before. And now we can totally anti-differentiate it. The antiderivative of this constant, as far as y is concerned, is just going to be, well, y times e to the x squared from y equals 0 to y equals 2x. I really do like writing parentheses around these. So that integral became this antiderivative evaluated between the two endpoints. And then we're going to plug in the endpoints and look what we get. We get the integral from x equals 0 to x equals 1. I'm going to plug in 2x for y. Minus, if I plug in 0 for y, 0 times whatever is just 0. And this problem has been specifically designed so that at this point now, we can make a really easy u substitution. What's a great choice for you here? What is a great choice for you here? Do you see something in this integral whose derivative is also there? Let's be simpler about it. You're not wrong, but I would prefer a simpler choice. Just x squared. You could picking e to the x squared will work, but it's I think usually easier just to pick the exponent, or at least do that first. So if we pick u equal x squared, our du is exactly 2x dx. So this integral becomes, now check this out. I'm actually going to change the limits of integration here, but they're not going to change at all, because if x is 0, then u is 0, and if x is 1, then u is 1. But I am going to write that because I want to be clear. So I'm going to go from x equals 0 to x equals 1. Now I'm going to go from u equals 0 to u equals 1 of e to the u du. Integrate, not very exciting. E to the u from u equals 0 to u equals 1. You could plug back in x squared and then plug in 0 and 1, but we could have also done that for the previous problem. We could have left it in terms of u. I just didn't want to there. So here we're going to get e to the 1 minus e to the 0, which is going to be e minus 1. And that's how much volume we have under this surface over that region. Oh yeah, cool. Thank you, Jocelyn. Yes. All right. We do another one? I think we should. Wasn't really a question. It was more of a prompt. Let's do one more. Okay. So let me give you all one. And I want both of you to try on your own interchanging the region of integration. So here is the problem we're going to do. We're going to do the integral from x equals 0 to x equals 2. And then from y equals x cubed to y equals 8. And the function that we're going to integrate, which you don't really need to worry about right now, is 9x to the 8th over 1 plus y to the 4th dy dx. So I'll even help you out. I'll draw the region. So our region is y equals x cubed to y equals 8. And then we're going from x equals, so this integral is written using what kind of strips? Does this integral use vertical strips or horizontal strips? Yeah, it uses vertical because you're going from y equals to y equals. So we've got our vertical strips from y equals x cubed to y equals 8. And then we're going as far left as x equals 0. And as far right as x equals 2, which is undoubtedly where those two things intersect. So there's our region. I want you to reimagine it using horizontal strips. And rewrite the integral with new limits of integration. Or I should say reversed limits of integration. I'll give you like 2 minutes to do that. You got it. Remember your name. Olivia. I was going to guess something totally wrong. Olivia. I think there's 2 Olivias in this. Or there's 2 Olivias registered for this class. Yeah. I've noticed because I've accidentally a few times marked the wrong person's attendance. I'm like, oh, I need to fix it. We're almost there. One thing I would say whenever I'm doing this kind of thing where I'm changing the order of integration, or really just with integrals like this in general, if I'm setting it up or changing it or whatever, I'm always working from the inside out. We're always working with the inner integral first and then the outer one. Because what's happening with the inner one kind of might determine what happens with the outer limits of integration. So for the inner integral here, the limits of integration are going to be from a left of x equals 0 to a right of this function here that we have to solve for x, which is going to be x equal to the cube root of y. Or y to the 1/3 if you prefer, which I kind of do. And then we're going as low as y equals 0, as high as y equals 8. And that's our setup. Function doesn't change. That's all. I felt like I had more to say there. That's all I had to say. Function doesn't change. The dx dy and the dy dx change the order. Just as a FYI, sometimes if people are writing this very generically, they'll just call this thing dA. Just for the change in area. Small change in x and the small change in y is a small change in the area. Just something to be aware of. So now let's find it. Because the whole point of this is now, so I should back up just a tiny bit here. The point of this is that just like before, if I were to separate, ooh, can you see that? No, you cannot. If I were to separate this into like the 9x to the 8th, which is a constant as far as y is concerned, times 1/1 plus y to the 4th, 1/1 plus y to the 4th is also a function that cannot be instantly differentiated. At least not without a whole lot of, it's probably actually not possible. But so switching the order of integration now makes things doable. Y equals 0 to y equals 8. X equals 0 to x equal to y to the 1/3. And I do like to break these apart so it's easier to see here. So I'm going to have a 1/1 plus y to the 4th times 9x to the 8th dx dy. So now we can totally integrate 9x to the 8th. That is something we are definitely capable of doing. And that 1/1 plus y to the 4th times 9x to the 8th, that 1/1 plus y to the 4th just gets to hang out as a constant multiple. So integrating, I get 1/1 plus y to the 4th times x to the 9th from x equals 0 to x equals y to the 1/3 dy. Plugging in, by plugging y to the 1/3 for x, y to the 1/3 to the 9th, you multiply those powers and you get 9/3, which is 3. So we have a 1/1 plus y to the 4th times y cubed minus 1/1 plus y to the 4th times 0, which I shouldn't have really written, but I wanted to actually. That's just 0, but it's good to make sure that you're checking out what happens when you plug in that lower limit. It's not always going to be 0. And now, just like the previous examples, we're left with a function that is easy to evaluate via a simple u substitution. So if I let u equal the denominator, which is 1 plus y to the 4th, that is a u, believe it or not. My du is going to be 4y cubed times dy. And if I divide both sides by 4, 1/4 du is equal to y cubed dy. So this becomes the integral 1/4 du. That takes care of the y cubed dy. And then my denominator is just u. Should I change the limits of integration or not? I don't actually care, but I'm really asking you all, what would you prefer I do? All right, I'll change them. So if we change them, y equal to 0 gives us, maybe I shouldn't change them. U equal to 1 plus 0, which is 1. And if y equals 8, u is going to equal a large number, 1 plus 8 to the 4th. Which we could figure out if we really wanted to, but we don't really want to. And then we do the integral. We're going to get 1/4 natural log of the absolute value of u from u equals 1 to u equals 8 to the 4th plus 1. Plugging in, we get 1/4 times the natural log of 8 to the 4th plus 1. I don't need the absolute value because the absolute value of a positive number is that number. minus 1/4 the natural log of 1, which is just 0. So we end up with just 1/4 times the natural log of 8 to the 4th, which is 4096 plus 1. I think. Pretty sure. But that doesn't matter, right? We could have just you could have just written it like this, and that would have been probably the better choice to make. All right. So that's pretty much most of it. Let's do one more. I got one more for you because there's one more thing you might get asked. Maybe not, though. That seems I'm a liar. I don't think that's true. I was thinking you might get asked about the average value. Remember average value from 17b? Maybe kind of. So let's just let me remind you. In 17b, the average value of a function over an interval is just the area under the function divided by the length of the interval. Or as more people write it, 1 over b minus a times that. You're essentially taking the total area and dividing by the length to say, well, if everything was at the same height, that would be the height you would get. Same idea is true if we add another dimension. Now I'm going to take some thing that has some volume under a surface and say, okay, well, if I divide that volume by the area of the region that it is over, then I could imagine all that volume being at the same height. And that height would be the average height of this double integral. I should say, better words, it'd be the average height of this function of two variables over its region of integration. So unfortunately, the calculation is a little bit less nice. And I don't actually know if you have to do this, so that's why I'm kind of hedging here. But if you were asked to find the average value of f of xy over some region, well, the dividing part's a little less nice, but the idea here would essentially be that the average value is going to equal the double integral over your region of your function divided by the area of the region, which is just the double integral over the region of 1. So that's how you would find average value. I think I'm not going to do that just because I don't want to do it and then be like, no, we have to do it. So next class we will talk about average value if we need. We solve 3. I feel like I should use all the time. I hate like not. No, I won't. I can let 3 minutes go. It's fine. So next time we may talk about average value.